Is this visible from the back? It looks a little small. You can see it? Okay. Okay. So we were talking about deadlocks. Okay, so I just want to reiterate for those of you who are distracted by the exam and so on. So deadlock is basically a condition when there's a group of threads or processes that are waiting to acquire a resource, and that resource is held by some other threads or processes in the group. So in some sense, each thread or process is waiting. They hold some resources, you wait for some other resources, the resources you wait on are held by others. So everyone is waiting for someone else, no thread or process can make progress. Okay, so that is what deadlocks are. I mentioned that deadlocks are different from starvation. Starvation is a condition where some threads are making progress, but in making that progress, you prevent other threads from making progress. So there was only a subset of the threads don't make progress as starvation. In deadlock, no one makes progress. Okay, that's the key distinction between the two. I mentioned the necessary conditions for deadlock. Okay, so there was mutual exclusion, there's hold and wait. Mutual exclusion simply means your code has to have locking or semaphores or monitors. Hold and wait is you hold some resources, wait for others. There's no preemption, which means that one thread cannot force some other thread to give up the locks it's holding. And last one is circular wait, which means, and if you actually analyze the hold and wait pattern, you will actually see a cycle in it. So if a deadlock has occurred in the system, all of these conditions will be true. Okay? And then we basically looked at a scenario where we saw this thing called the resource allocation graph, which is a data structure that maybe a kernel or a synchronization library can use to track which threads are holding what resources and which threads are waiting or trying to acquire what other resources. And we said if you could run a cycle detector on this graph to detect cycles, which may be indicative of a deadlock. Okay? And that's where we left it. So what we are going to do now is look at the other side of the picture, okay, which is called deadlock prevention. So whatever we talked about is deadlock detection. You look for deadlocks after the fact and try to fix the problem. You let the threads or processes contend for resources. Every once in a while you check for cycles, and if you see a cycle, then you try to fix the problem. Deadlock prevention tries to do something beforehand. You do runtime checks before you grant locks or semaphores, and make sure that you will never even get to a scenario where a deadlock can occur. Okay, so one is trying to fix the problem before it occurs. The other is trying to detect the problem and fix it after it occurs. So now we are going to look at deadlock prevention. So how do you go about preventing deadlock in the system? Okay, so we said there are 4 necessary conditions for a deadlock. If one of them is, if you impose some constraints such that one of them is false, then it follows that deadlock cannot occur. Okay, because if a deadlock occurs, all of those conditions are true. But if in your system one of those conditions can never be true, then that follows that deadlock could not have occurred. Because if it had occurred, that condition in addition to the other 3 must have been true. Okay? So the idea is to impose some constraints or do some runtime checks such that one of those 4 conditions is false. Okay? Now you could have any number of techniques to prevent deadlocks. Okay? And those techniques would make sure one of those conditions is false. So let's go and look at which one will make sense for us to look for in terms of deadlock prevention. The first one is mutual exclusion. Okay? You could say, have a system that says you may not use any synchronization. So in this system, there is no mutual exclusion. If you say you cannot use locks, and there cannot be any deadlocks, it follows from that. Clearly, there's no locking going on in front of deadlocks. Now that's a very harsh condition to impose. It implies that you can't have any synchronization at all. But that's an example. If you have a constraint you want to make false, then you will not get a deadlock. So you won't go with that one. That doesn't make sense. So the other issue is you can try to avoid, let's say, no preemption. And you can say you relax the condition where you cannot forcibly take a lock from some other thread. Okay, so you can say some threads which may be more important can force other threads to give up their locks. Okay, so you could have a system like that. Again, there won't be any deadlocks because there is a circular wait. The most important thread will force some other thread to give up the lock and the cycle will be broken. Okay? So you could have a system that does that. But now that makes your code more complicated. You don't expect to say lock acquire and you're in the middle of a critical section and suddenly you're being forced to give up a lock by some other thread. Okay? So it's not going to actually make your code work very well if in the midst of critical section some other thread or entity is forced you to give up the lock. Okay? So you don't want to have a scenario like that either. Okay? So what we could do, however, is prevent circular wait. Okay? So whenever you have a lock acquire request, we will check that if this request were granted, would that result in a cycle in your graph? Okay? If the answer is yes, then you will actually not grant the request even if the lock is free. Okay? You will say that this could put the system into a what we call an unsafe state, which may result in a deadlock. So I'm going to do this extra check beforehand to see if this lock request were to be granted, would it result in a cycle? And you try to make sure that any grants of locks never get into a cycle, in which case if there's no cycle, there is no deadlock. Okay? So that's the condition we are actually going to use to implement our deadlock prevention strategy. Is that clear what I just said? So you can have any of these 4 conditions be false in your system, and in that case then you cannot do deadlock in the system. And it looks like the most reasonable one to go after is trying to prevent a cycle, okay, by delaying some grant request. Okay, so just by delaying a grant request, nothing bad has happened. The thread just has to wait for a longer period of time, and you grant it only when there is no other cycle you can see in the graph. Okay, by granting it. Okay, so we'll look at how to go about doing that. I'm going to present two techniques. Okay, first I'm defining some terms and then I'm going to present 2 techniques. One is simply a simple runtime check. The other one is called the banker's algorithm. Okay. So the first technique is basically going to depend on cycle detection and our resource allocation graph. But let me first define some terms. Okay. So we'll distinguish the system being in a safe state versus an unsafe state. Okay? So a safe state is one in which there is at least one sequence in which each thread is allowed to execute, finish execution, give up its resources, and the next thread runs and so on, and they all finish. Okay? So if your system has at least one order in which the threads can go one after another and finish, it follows that there couldn't have been a deadlock because there's a way in which they can all execute and finish. And in contrast, an unsafe state is one in which there is no order, in which the threads can actually execute and finish, in which case it means that you may be in a deadlock. So what we want is if your system is in a safe state and your some thread requests a lock, you want to only grant that lock if it keeps the system in a safe state, which means all the threads can make progress and they can finish. If you see that granting the lock puts you in an unsafe state, and we see examples of unsafe state, then you don't want to grant that request. Okay, so this algorithm is going to ensure that you don't go to an unsafe state by looking for cycles. Okay, I'm going to give you a more algorithmic description of the technique rather than looking at cycle detection, but you can implement that by cycle detection as well, as you will see in the next few slides. Okay, so here is an example we'll work with. Okay, so here we will assume multiple instances of resources. This is the more general version of the problem. So let's assume there are 3 threads, T1, T2, T3. Okay? And they are competing for tape drives. Let's say these threads are backup processes. They're backing up some data from a machine to a set of tape drives, which are just storage devices that hold backup data. Okay? And we'll assume there are a dozen tape drives. Okay? And we'll assume that the thread can actually write data to multiple tape drives. So it can request multiple tape drives. And a tape drive, if you know what a tape drive is, it's actually a system that only one thread or process can write to. Unlike a disk, multiple processes cannot issue concurrent write. So only one thread can write to a tape drive at a time, which means you need a lock on the tape drive and only that thread can write to a tape drive. Okay. So the scenario is actually current system scenario shown in the table. What it says is T1 can request up to a maximum of 4 tape drives to write to while backing up its data. T2 can request up to 8, and T3 can request the entire set, which is a dozen tape drives, okay, to do its backups. Okay? And the next column there, which is the in use. So this is the max need column, which says what is the maximum resources you can need. This second column says what is the thread currently using. Okay? But just because you could ask for the max doesn't mean you have to. There may be scenarios where you are actually using a smaller number of threads. So it says T1 is currently using 3, T2 is using 4, and T3 is also using 4. Okay? And this third column is simply saying what's the difference between the two. So it says what more are you allowed to request based on that max. So it's just the difference between what is the max you can request and what is it that you currently hold. So that's the could need column or the need column. So now the question is, what's the worst case scenario that could occur in the system? And even in the worst case scenario, could all the threads actually run to completion without blocking for other resources? So one possible worst case scenario is every thread suddenly says, I want the maximum that I said I could request. Okay, so all three of them come and ask for the max. Okay? And clearly there aren't, you don't have enough tape drives to satisfy all of them all at once. Okay? But the question is, can you satisfy them one at a time and let them all finish? Okay, if so, you have a safe state because it says that there's at least some order. Even in the worst case scenario where all the threads are requesting their max resources, is there a way by which they can execute one at a time, go to their max, finish, release those resources, give them to some other thread that takes up its max and so on. Okay? So if you analyze this scenario, the question is, can these threads actually finish one after another in some order? And we have to determine that order. If we cannot find one, we'll say it's an unsafe state. Okay, so let's analyze this a little further. Okay, so so now I'm going to suggest that the current state is safe. Okay? And that what that means is we have to find some order in which they can finish even in the worst case scenario. So the question is, how do we go about figuring that out? Yes, something to say.
When we look at these sorts of possible resource orderings, do we discount the fact that the thread could abandon its current resources?
The question is, when you do this, do you actually ignore that you could abandon? So we assume that in the worst case, you are going to ask for everything. But if you could certainly, in the course of execution, give up locks, acquire other locks, and things like that. But we are saying what's the worst that could happen is you hold everything and you ask for everything else that you could possibly ask for. Okay. So yes, so I think you could certainly give up resources, but that won't put you in the worst case. So you want to consider a scenario where everyone is being greedy and doing the worst possible thing, which is you just get a request for all of the resources.
Would you do the shortest job first?
Okay, question is, could you do a shortest job first? So we have to analyze the scenario and find an order. It doesn't matter what the order is. So let's look at what is the current state. Okay, so we have a dozen resources, a dozen tape drives. Okay, so if you see what is in use, you will see 11 of them are in use, which is 4 plus 4 plus 3. Okay, so of the dozen, 11 are in use, 1 is free. Okay, so that's the current state of the system. You have dozen resources, 11 have been allocated, 1 is free. And now we have a scenario where each thread is asking for its max, which means T1 asks for one more tape drive. It has 3, it could ask for 4. T1 asks for one more, T2 asks for 4, and T3 asks for 8. The question is, can we let them execute in some order? Since you have one tape drive remaining, the only request you can grant at this point is T1's request. Because you have one, it asks for 1. So you give that 1 to T1. So now it has the maximum it could need, it has all 4. So it can execute to completion. It cannot ask for any more resources at this point. If you gave it the worst case scenario that it could ask for, it should be able to finish. So let's say T1 runs to completion. Okay, T1, that backup process finishes. Then it's going to release its 4 tape drives. Okay. Now you have 4 available. So you look at what other threads request could you service at this point in time. And we'll see that T2 could ask for 4, and in the worst case it has asked for 4. So you give all of T1's tape drives which it has released to T2. Okay, so now T2 has a max it could need. It's going to run to completion, and it will release all 8 of its tapes that it was holding, and then you can actually give them to T3. T3 is going to run to completion. Okay? So we found one sequence. It doesn't matter what the sequence is. Okay? So long as you have at least one, let's say this system couldn't possibly deadlock. Because they all asked for the worst case. Even in that worst case, I could actually make them all run to completion in a certain order. Okay? So they will be able to finish even in that scenario. So you basically say the system is safe because this couldn't possibly result in that. Okay, is that clear? Any questions on this? So the job of the deadlock prevention algorithm is to actually find that sequence if one exists. So what you're going to do is you're going to have a search algorithm that says, what if you gave resources to this thread, and this thread? So you look at various sequences, and if you find one, you are good. If you don't find any after all the searching, okay, you say there is no sequence that I can find where I can satisfy these threads and let them finish, then you say the state is unsafe because you may actually get a deadlock. So you cannot find any way in which they will finish. Okay, is that clear? So we haven't seen how to do the search. I just explained the idea at this point. So I'm going to elaborate on that a little more. Okay, so now let's say here is a different scenario where from the previous scenario, okay, T1 asks for one tape drive. Okay, let's say you grant that request. Okay, so the only thing that has happened is there were 11 in use. There's one free. T1 asked for the one more it could ask for, and you granted it. Okay, so let's see where you. So now if you have 0 tape drive available, each thread can now ask for more, okay, and then there is no way to satisfy. Okay, so you make this check and you figure out should you grant that request or not. Okay, so now with that background, I'm going to show you a little more details of how you may do this using two different techniques. One is a graph technique, the other one is a matrix-based technique. Both of them will achieve the same purpose. Okay? One is more visual to understand, the other is more mechanical. Okay? So let's look at how do you do whatever I just said using just looking at a graph. Okay, what is this unsafe state? Can we reason about this just from a graph rather than looking at resources? So here is our resource allocation graph. Okay? Circles represent threads. So there are 4 threads, T1 to T4. Boxes represent resources. Again, there are 4 resources. Okay? And I said there are 2 kinds of edges, if you remember last time, for those of you who had come to the lecture. See, there is a directed edge going from a resource to a thread. Okay? That essentially means that resource is held by the thread. Okay? If you have edges going from threads to resources, like a T2 to an R1 thread, okay, that means that thread has requested that resource, it's not holding it. Okay? So an edge going from a resource to a thread means the thread holds that resource. So an edge going from a thread to a resource, it means you have requested but you don't have the resource, you're waiting on that resource. Is that clear? What the 2 types of edges are? So we are going to now add a third kind of edge, which are these dotted edges. Okay. So whenever you have new lock acquire requests, we are going to add a dotted edge and analyze the graph to see if it actually results in a cycle. Because if you actually went ahead with processing that request, then that edge would actually be a solid edge. Here you're just doing a check before you even go forward. So what would happen if you added that new edge as a result of that lock acquire? Okay, it could be an edge in either direction, depending on whether the thread is, or whether the resource is available for this thread or it's in use. Okay. So in this case, our unsafe state is simply one where a new lock acquire request come. Before you even process the request, you add a dotted edge to the graph in either direction, depending on whether the resource is free or not. And then say, does it actually, and then run your cycle detector. If your cycle detector finds a cycle, you said, if you actually grant this request, that dotted edge will become solid and you will actually have a cycle. So you won't grant it. On the other hand, if the dotted edge doesn't show you any cycles in the graph, then you say it doesn't matter. So we are going to just let it go, we let it through, and that's going to not cause any cycles in the graph. Okay, is that clear what I said? Let's not look. Okay, so you have a resource, just to recap, you have a resource allocation graph that shows you the current state of the system. which is what threads are holding what resources and what resources and what threads are waiting on what resources. If a new request comes in, before you even process the request, you are going to see what does that request do, what does that new edge do to my graph. If that new edge is going to cause a cycle in the graph, I say that is going to put the system in an unsafe state, so I shouldn't let this request go forward. Okay, so that's your runtime check to do deadlock prevention. Yes? Question?
In this example, if both of those dotted lines become solid, would that be considered a cycle?
In this case, first of all, you can't have both of them becoming solid because that would mean both of those threads hold those resources. So here what has happened is these two threads are requesting that resource. Right? One of that resource is free currently. One of them is going to get that resource. Other is going to wait. Okay? So now let's take the scenario where this thread actually waits and that resource is allocated to that thread. So if they are solid, both will be solid. One is going to wait and the other is allocated. That is going to result in a cycle. Did you get that, or should I repeat what I said? So these won't become solid in the direction they're pointing. So this is just showing a scenario where two threads are trying to acquire a lock on that resource. They're contending for the lock. Okay? That is why there are two dotted edges.
So what will happen is one of them will become a solid line pointing to the resource. The other one will be the resource is assigned to the other.
Yes. So if you let both of them go forward, one of them will get the lock, the other one will wait for the lock. They will both be solid, but one will point towards the resource, the other will point away from the resource. And if you let that happen and that introduces a cycle, in particular, if your solid arrow goes this way and this way, that's a cycle. So then you don't let that happen. So that's bad, because you will actually get into that. Is that clear? So this is showing two concurrent requests coming. You may have only one request coming in and you can do the same analysis. Say if that dotted arrow became solid, what would have happened? Any questions on this? Yes. Yeah, it could go the other way. Then there's not a cycle because they're directed graph. So they're both contending, and if the lock gets granted in the other way, the other thread gets it, then you will not get a cycle because it has to be a cycle in a directed graph, not an indirect graph. So that's still a safe state. Okay. Is that clear? That was a good point. So in this case, the order matters whether you get a cycle or not.
So would this be considered an unsafe state?
Sorry?
Would this be considered an unsafe state?
Right now, without these requests, this is a safe state because there is no cycle. If both these two requests came in and you granted it in the order that introduces a cycle, that's unsafe. If you grant them in the other order, that's safe because there's no cycle. Okay. Okay. So we'll now look at, so that's a deadlock prevention technique. They're simply looking at graph and looking for cycles in the graph. Okay, that works when you have single instance of a resource. The general case, which is a tape drive example I was showing you, I said there are multiple instances. In that case, there were a dozen of those tape drives. Okay, so that has to be handled slightly differently. So there's a more general version of the cycle detector, which is called the banker's algorithm. That works whether you have one instance of a resource or n instances of any resource. Okay, it's a general scenario, and we'll look at what it does. It's doing the same thing essentially. It is going to look for what would have happened if I granted this resource. Will that be a safe state, which is equivalent of, is there a cycle somewhere if I granted it? If by granting it, you see the equivalent of a cycle, you say that you don't grant it. Okay? And the way we'll look for that is to find an order or a sequence in which some threads can finish. I'm going to show some pseudocode of how this is going to work. Okay? And then we'll look at two examples of so this is banker's algorithm, and this is simple pseudocode. When we'll maintain two matrices, okay? There is that max matrix, which is going to say what is the maximum number of resources a thread can request. Okay? There is an allocation matrix, which is what has been allocated, what is in use in my system. And then there is a need matrix, which is how much more can each thread request. Okay? So let me just preface all this by saying to implement this algorithm, okay, when your process starts up, it has to somehow tell the operating system or the runtime system that implements synchronization, saying what are all the resources you could request within your code. Okay. Now this could be, clearly a process is not going to tell the operating system. What you will have to do is analyze the code. Let's say you're given the source code. You look for every possible lock, acquire, request statement in your code and say, in the worst case, all of those locks could be used at the same time. When you say, so this is my worst case, I'm going to acquire locks on 6 different variables, and these are all the locks I could acquire. So this has to be specified for this technique to work. Yes, question. Why do they have 2 dimensions? Okay, so I'll talk about that. So one dimension is processes. So you keep track of it for each process. And then the other dimension is the process. We are assuming that there could be multiple instances of a resource. So you can have a process saying, I need 2 tape drives. Right? So that's why there are 2 dimensions. So for each process, you track how many resources of each type could be requested. Right? So in the simple case, there's only 1 resource of each type. So then you only need 1 dimension, which is each process says which resources are you going to request. Okay. Any other questions here? So I'm going to show you some examples. So there are 3 matrices here. The max matrix that says what is it that you can actually request in the system in the worst case. The allocation matrix is at this point in time, at this point in the execution. What are all the resources that have been granted to various processes or various threads in the system? That's the allocation matrix. Okay? Need matrix is just going to be the difference between the two. It's like I said I could ask for X. Currently I hold Y resources, so I can ask for X minus Y more resources. Okay, so that's going to be the need matrix. Okay, so I don't know if you can see this in the back. It's a little busy. But here is basically the code. So that's your allocate. Okay, so first you're going to do some error checks, saying if your request for asking for more resources, okay, that's the acquire request. Ask for more than what you declared at the beginning, that's an error. Okay, so that's the first statement saying if request is more than need, then you are asking for more than what you said you would possibly ask for. So you just deny the request, saying there's some error of some sort, and then if what you're requesting is greater than what's available, then you say that there isn't enough in the system. So you clearly have to wait. I'm not going to worry about granting any resources at that point. Okay? And then if neither of those 2 things are true, that says that there are enough resources currently available to grant this, grant the request. Saying it's equivalent of saying the lock is free. Okay? So now you say if I grant the lock, does it cause a cycle? That's the equivalent check we are going to do. And that is basically this check here saying, you're going to call this function saying, is this a safe state? And that function is actually on the next slide, which is essentially a big search function. Okay, that code is not real code. It is simply saying if, so what you're going to search for is say that is all of the other threads also make their worst case requests. Okay. Is there a sequence in which they can all finish one after another and complete? If so, you are in a safe state. If there is no such sequence, you are in an unsafe state. That's the basic idea behind Ranker's algorithm. Okay. So that while loop there is simply doing a search. Okay, find a process. So you're saying, is there a process that can complete? Okay, then you let it complete, and then you say, let's assume it releases its resources. Is there another process that can complete given the resources it just freed up? And you let that process run and so on. So you try to just search for a sequence of processes. Yes, question. Yeah, you could potentially search for all possible as exponential, so that's very bad. So the complexity of this technique can be high unless you actually have a better way to search. I didn't show the exact search algorithm. I just said find a process that can finish. Depending on how you find it, this could have exponential complexity or not exponential. The goal to want exponential. Okay, that's like saying I do a brute force search, which is really not the right way to go about doing a research. Okay, so still this is an expensive algorithm. It can require order of m times n squared. Okay, that's the complexity. N is the number of processes, m is the number of resources. Okay, so quadratic complexity. So lots of thread, lots of processes. This algorithm is going to take a long time. Every time you do a lock acquire, it's going to sit and do all this search between all these processes and all these resources and say, is this going to be safe or not? So it is quite a bit expensive to run. Nevertheless, that's the way the technique works. So we'll just work to an example just to see what we are going to just solve. Okay? So here is the current snapshot of our system. Okay? Now you will see why there are two matrices. Okay? So this column is the max matrix. Okay? So we'll assume 4 processes P0 through P4, 3 resources A, B, and C, and we'll see that there could be multiple instances of each resource. There could be 3 of A, 2 of B, whatever it is. Okay, so what A, B, C are, we don't care. Okay, there are some resources. Could be tape drives, there could be variables, there could be data structures. Doesn't really matter from our perspective. So we'll treat them in the abstract. Okay. So when each process starts, it declares a vector saying what is the worst case resource it can request over the course of its execution. So just if you look at P2, P2 says I could request 2 of type A, 3 of type B, and 5 of type C. That's what it has declared to the system. And it's going to be held to that. Can't give it more than what it said it would request. Okay? So each process is going to declare that to the system. And as I said, typically the way you will do it is you will analyze the code and look for all the acquires in your code and say, let's assume they are all asked for at the same time and say that's my worst possible scenario. Okay? You could do smarter things than that, but that's one way to do it. Okay? This column here is showing you the allocation matrix, which is what are the resources that have currently been granted and which process is holding what. So if you look at any of these, you'll see that in this case P0 or rather P3 holds 0 of type A, 6 of type B, and 3 of type C. Okay, so that's what is actually used in the current point in time. Okay. Available, we are going to fill up. So this is our current snapshot. This is what each process said it would do, and this is basically what has been allocated. So we'll analyze. Let's first analyze this state and see, is this even a safe state? Should we have even gotten here to begin? Okay, so let's ask some questions and try to understand what's happening. Okay. So first, there are 3 questions that you need to answer to understand whether the state is safe. So first, we are going to ask what are the number of resources in my system of A, B, and C. We are going to compute what is called the need matrix, and then we are going to ask, is the system safe, which means every process comes and asks for whatever is remaining in its need matrix, and that's your worst case, can they all finish in some order. Okay, so let's answer each of these questions in turn. Okay, the first question is, how many resources do we have in the system? Okay, of type A, B, and C. Yes.
3 of type A, 14 of type B, 11 of type C.
So the way you figure out if this is the system snapshot that has been presented to you, you basically, this is our available matrix. This is what's available. This is what is in use. Okay. So if you sum the two, you should find the total number of resources. Okay. So you say I have 10 available, 2 are in use, so then you have 12 resources. So you're simply going to take the total allocation and the total available and sum it up, and that will tell you how many resources of each type. That doesn't tell you anything interesting, but that just allows you to figure out what's going on. Okay. Second question is, what is the contents of the need matrix, which is how many more resources could each process possibly ask for. Okay, and that is, again, if you look at this matrix, you should be able to figure out, given what you said you would ask for and what you currently have in hand, what more could you ask for. Okay, so question is, how do you go about doing that? You will take the max and you will take the allocate and you will take the difference of the two. Okay, if you said this is the max you could ever ask for, this is what each process holds, and what more could it need? Okay, that's the difference between the two. So typically the need matrix is the difference of the max matrix and the allocation matrix. Okay? Then we'll ask the third question of how do you go about figuring out that's a safe state or not based on the need matrix. Okay, so I'm going to show you the answers to those questions as well. So basically the contents of the need matrix is max minus allocate. So this is what you can actually ask for. Okay. So now the question is it safe? So to understand that, you say let every process come and ask for whatever more it needs. Okay, so this is our worst case scenario. So P1 is going to ask for 7 of B and 5 of C. P2 is going to ask for 1 more of A. P3 is going to ask for 2 more of C. That's the worst case scenario you could see in your system. Question is, can they all still execute and finish in some mode? Okay. The answer in this case is yes, but then we have to ask why is it yes. So let's say what could happen in the system. So you will note that in this case P0 cannot ask for anything more. It already holds the max. So that should be clear from this matrix. It said it could ask for 1 of C, it's holding 1 of C. So there's nothing more it could ever ask for. Okay. So P0 can run to completion at this point. Okay. So if it runs to completion, then it's going to release that 1 of C it is actually holding. Okay. So that goes back to the available pool. So the available pool is going to increase to 153. Okay, because these are the resources that are available. P0 can finish. There's nothing more it could ask for, even in this worst case. So you will have 1, 5, and 3. So if you have 1, 5, 3, what can you do? Okay, so can you actually let some of these finish next? Okay, so I'm going to write. There's no chalk here. So let's assume you have 1 of A and 5 of B and 3 of C. So which process could go next?
P2 could go next to by using one of A.
Okay, so P2 can clearly go next because it could ask for 1 of A. Even without P0 going, there is already 1 available. Okay, so P2 could go next. If P2 goes next, it's going to then go ahead and release all of the resources it held. Okay, so you'll return that 135 to the system. So you will now see that you have enough resources. In fact, you will see that P2 could have also gone next because you had 2 of C already available. So if P2 does go next, it's going to release those resources. You can run P1 to completion and P2 to completion. Okay? So in this case, there are multiple possible ways by which they could finish. Okay, so you are not in unsafe state at all. It's not just one, but many different sequences in which case you could still guide everyone the worst case request they could make and let them all. Okay, is that clear? Yes. So now I'm going to give you another quick. Okay, so here is the next scenario. So we'll assume the current system state, which we know is safe. We just analyze and said it's safe. So now it's a request from P1 arrives, which is going to ask for 052. Okay. The question is, should you grant this request or not? Okay. And the answer to the question is going to be, we'll assume that you granted it. You look at what the system state would be if you granted it and ask if that state is safe, just the same way we did the analysis. Okay, if that new state is safe, then you should say fine. If I go ahead with this request, it's still going to leave me in a safe state. If you say it's unsafe, then you say I can't grant this request. Okay, so you pretend to give the process what it asked for, analyze, and then say is it safe or not. Okay, so we are going to redo the same example. Okay, so I'm going to just show you rather than working through the details. So here is basically the state of the system if you granted that request. So if you just go back to what happened. Okay, this was our current state, and P2 has asked for, or P1 rather has asked for 052. So that's what was the thing. So you basically say that's what you give to this P1 process, and then you look for the system state. So I'm flipping back and forth, but just so that you get the idea. So if you go ahead with that system state and give P1 what it asks for, this is what you have. Okay, so that's your allocation, that's the max matrix. Now what is remaining is 100 in this case. Okay, because all of the type B and type C resources are in use. Okay. The question is this a safe state? And what is the sequence in which they can finish? Yes.
I think it's still safe. At least for the first when you probably finish process 2
Okay. Okay, so first you should realize that you can always let P0 finish, already holding the max. Okay, so it will run, it will release one of C, now you have 101. Okay, so that's what you have. Okay, then you say what's next? What can go next? You will see that P2 can go next because P2 can ask for one more of A. It already holds the max of B and C. You can ask for one more of A. You do have that one more of A. So you can let P2 go next. Then it'll run and actually release 2, 3, and 5. So that's a lot of resources that get released. And as a result of that, you can now satisfy either P1 or P3. Okay, they're enough to have either of those to ask for the max and satisfy. Okay. So what this tells you is if you got a request from P1 for 052 more resources, you could actually grant that request. It will put the system into this new state, and this new state is also safe because even in this new state, if additional requests come, where everyone asks for their max, everyone can still finish. Okay? And that's essentially what that banker's algorithm was doing. It said, let's grant the request and let's search for these sequences that we have just worked out by hand. Okay, so it will find this sequence and say this is a safe state, so it's okay to grant P1 its request for 0, 5, and 2 more resources of A, B, C. Okay, is that clear? Right, so now I'm going to just tell you a few more things. Okay, so I'm done with deadlock, but there's a couple of takeaways I wanted to point out before wrapping this up. Okay, so we went over what is deadlock, and it said there are two possible techniques. Okay? One tries to do these checks before the fact. You run cycle detectors, you run banker's algorithm, say, is my system in a safe state? If so, you grant the request, otherwise you say no. That makes sure that there will never be a deadlock. Okay? The other technique says, let's not worry about any checks beforehand. Let the processes do whatever they want. But every once in a while, I'm going to look at the resource allocation graph, see if there is a cycle. If so, you go and terminate those threads and breaks. These processes are deadlocked, there is no hope for them. The only thing you can do is terminate them and restart the application. You go ahead of saying, I reboot my system. Okay? So those are two possible scenarios. And now, as I also mentioned when I started talking about deadlocks, although it's an important problem to not have deadlocks in the system, okay? Most operating systems do not actually implement any of the methods that I talked about. Okay? They just leave this to the programmer, saying these are all expensive things to do. You run a cycle detector once a minute, or you run banker's algorithm. Every time there's a lock acquire request, you go and run this expensive algorithm to grant a lock. And that's very expensive to run. So most operating systems would say, not my problem. If you wrote bad code that gets you into deadlock, you deal with it. Okay. So it's often left to the programmer to write code that is not going to actually have any scenarios where it's going to be result in a deadlock. Okay. So when you write your code that has all these locks and semaphores, if you write it well, you can actually guarantee there is no deadlock. The real question, which is not material here, is how can you always ensure that any code you write is deadlocked? No matter what happens, how the threads run, how the threads get scheduled, you shouldn't actually have have enough resources on the thread. That would be great if there no resource retention. But let's assume that you have some number of variables and you need locks only. Yeah? So there are some order in which if you grab locks, you will have deadlock. In other orders you won't. And in particular, if you go back to the very first slide, okay, so I'm just going to give you a very tiny example. So this was the very first slide I introduced to show that how deadlocks can occur. You have two resources, printer and disk, and both processes have to grab a lock on both of those resources to, let's say, print a job. And process A gets the printer lock first and the disk lock next, and this one gets the disk and the printer. So you could have a scenario where each process gets the first lock and is waiting for the other process to release the lock. So that's a deadlock. Okay? So another way to ask that question is, what modification could you do to this code so that there can never be a deadlock? Okay, but that get is doing the same thing. You need to grab two locks. And this code can get you into a deadlock. But you can make modifications to the code that doesn't get you. So you wrote deadlock into this. You can make them symmetric. So if you actually swap process B and you make it get the printer first and disk first, they are both doing the same thing. The claim is in this case you will not have the deadlock. Okay, so one of them, both of them are contending. One of them will win. Let's say you get the disk down. Process A gets the disk lock. Process B starts up, it's immediately going to block because process A has it. Okay. So now this code you could fix this very simply by saying let's make it symmetric. But what is the principle that we use to make this work? Okay, so if you use that principle in any of your code, you will never have it. So what did we do that actually helped us? So when we imposed an ordering, okay, in particular what we did is we eliminated circular weight from the code. Okay? So as I said, there are 4 necessary conditions for a deadlock. One of them is a circular weight. If you write your code so that there can never be circular weight, you cannot have threads waiting on one another and they are in the cycle, and it follows you will not have a deadlock. Okay? So the question is, how do you eliminate circular weight? A very simple rule of thumb, okay, is if you have n resources, all of which are protected by a lock, you number them in some order. Doesn't matter what order, pick an order. You just number them 1 through n. And at any point, if you have to hold multiple locks, always acquire the locks in increasing order of their IDs. Which means that if you need a lock on resource I and resource J, let's say resource 10 and resource 13, you should always get 10 before you get 13. You always grab locks in increasing order. And then the point, the insight is if you do that, you will never have a circular weight. So clear why? So I'm simply saying, here's a rule by which you write code from now on. You have locks in your code, number the locks. Pick a number for each lock in increasing order. Okay. And if you have to hold multiple locks at any given point in time, just ensure that your code always acquires the lower numbered lock before it acquires a higher numbered lock. And the point is, if you do this, you shouldn't have circular weight. Question is why? Yes.
Because if you have log n and log n plus 1, and since you have log n, you must have logs 1, 2, and minus 1, and so no other log can hold n plus 1 if it doesn't hold other logs.
Okay, so you're sort of getting there. Not quite. But yeah, you are on the right track. It's something to do with ordering. Yes. Okay, so yes, something more to add.
Basically, it poses a pseudo-symmetry. In my point of view, I think it poses a pseudo-symmetry by saying that if 2 processes want I and j, I less than j, then both processes have to go in the same order to check. So we will never have that process A, thread A and thread B, both wanting the same resources, get them in the opposite manner, and then have, well, they end up in deadlock.
So I think you are very close. So I'm going to just argue this in the half minute I have left by giving you a sort of a proof by counter example. So let's say you wrote this code and still there was a deadlock. Okay? So if there was a deadlock, that essentially means that there is at least one thread, okay, because you have a cycle. Okay? There's at least one thread that's holding a lock on a higher numbered resource that is waiting on some other thread that holds a lower numbered resource. Okay? Because deadlock means there has to be a wrap around. Okay? If you acquire locks in increasing order, you will have a chain. But for the cycle to occur, there must be at least one thread that's holding a lock that some previous thread in the chain holds. So that essentially means you violated your rule, which is I acquired the lock in increasing order. Okay. The same thing is true here if you number the resources 1 and 2. Okay. Thread A, process A got lock on resource 1 and then 2. process B has violated that rule, is actually getting a lock on 2 and then getting 1, which is why there is a wraparound in a deadlock. If it was a chalk, I would have gone a nice figure here, but it seems to have efficiency in chalks for some reason. But the basic point is, if you actually acquire locks in increasing order, you can never have a thread that is further higher up in the chain ever waiting for a thread lower down the chain. That can only occur if I have a higher numbered lock and I'm waiting for a lower numbered lock. So that's the only way that can happen. But if you're actually acquiring them in an increasing order, you eliminated circular wait, because you can only hold lower numbered locks and you're waiting for higher numbered locks. So that can never cause a cycle in your graph because of the simple. Right? So the point I'm trying to make is OS is not going to give you any of these protections or deadlock detection. You are on your own to write deadlock-free code. And there's a very simple rule to write deadlock-free code, which is you basically make sure there can never be circular wait. And the way you do this is you basically order the locks or any resource that you're acquiring in some mental order in your code, and make sure if you ever have to hold multiple locks, if you only hold one lock, this is never a problem. But if you have to hold multiple locks, then you get them in that order and always in that monotonic order, not in opposite order that will make one thread wait on another and the other one is waiting on a lower numbered resource from other thread. If you do this, you eliminate cycles in your code, and then you will never write code that has deadlock. So that's the real takeaway from all of the material in deadlock. It's not all of these things, but how do you use these ideas in your code? Because in this case, the OS is not watching out for you. You have to watch out for yourself. Okay, so let's end it here. We will resume next Thursday. Okay? Tuesday is a Monday schedule, so there's no class on Tuesday.